Hello, YouTube! Today we're going to kick things off by starting about, honestly, just a lot of vocab. The basic point of this entire class is to get progressively better at modeling where everything is in the universe at all points in time under increasingly complicated circumstances. And if we're going to do that, it's probably pretty useful to start out by just sort of saying, well, let alone making all these complicated models to make predictions, how do we even describe it in the first place? And that's our goal today. So in particular, if you're good at describing the motion of objects using the vocab we talked about, you're in great shape. We're going to be using velocity, displacement, acceleration, speed, and the other big one would be distance and position. And if you're able to actually use those, and then in particular, if you can describe the ways that those things are related to each other, you're in pretty good shape. So I keep forgetting this. These have little animations on them. Position is where you are, and in particular, if you want to establish a position, the problem is that things in the universe are going to have some ambiguity unless you're really careful. So if I try to describe to you where I am right now, I can't really do that just by saying, like, I am in my house in a chair. You wouldn't be able to get to my location 100% of the time if you had that. Now, what I could do is give you a GPS coordinate, in theory, if I knew it and wanted to dox myself. And from that GPS coordinate, you could get to me. But there's sort of a couple things going on with that GPS coordinate. Otherwise, what I could do is I could sort of give you an address and say, start at this door. And from there, I could get you a set of directions to get to where I am. So I guess go up the stairs and it's the first room on the right. Once you're in that doorway for that room, turn 30 degrees to the right and you'll at least be looking at my location. But the problem here is you won't be there yet. I then have to say something along the lines of 3 meters, walk about 3 meters. At this point, you would be able to actually arrive at my location. There were 3 essential things I had to do there. If I just said, turn 30 degrees to the right and walk 3 meters, you would be nowhere near my location because you wouldn't actually have started at anywhere near the right place. So you need to make sure that you're starting at the right place. And what that's called is a reference point. And it's not necessarily that the reference point is the correct place to start. It's just the place that you've chosen to start for establishing any given reference frame. So somehow you're going to have a reference point in there. And that'll be what everything is relative to. From there, if I just said turn 30 degrees to the right, again, you're not at the location even if you're facing the right way. So we need to tell you how far you're supposed to travel. So there's going to be a distance associated with it in some way. And finally, you're also going to need to give that direction. If I just said go 3 meters, there's an entire circular radius that you could be in and not actually at the correct pinpoint. So you're also going to need a direction there. Anytime you want to give a position, you're going to need those 3 things. Normally, the reference point is sort of implied to be whatever 0, 0 is based on how you've set things, so you won't super have to pay attention to it, but it is always low-key there. So one quick thing about this is that you've probably heard the word position, right? A lot of physics words are going to be like that. They do mean things outside of the class. Inside the class, they mean something hyper-specific and very technical. So a lot of the times when you're talking about something going fast, if you're talking about something being slow, just be careful for those 2 in particular, because depending on how you're using it and what you're applying it to, people's heads are going to typically make some assumptions that aren't necessarily true. The other really big one is force or push. People associate a lot of things with that aren't actually really happening. It's just sort of our heads are like, whatever, this is probably right. If you then want to talk about something moving, it's suddenly a lot harder than just where something is, especially if it stays there forever. And the big reason for this is, let's say you've got 2 ways to travel. The first one is you start here, you go in a loop, and you end here. Now, these 2 things are separated from each other by, let's say, 5 centimeters. So you've gone 5 centimeters to the right from where you started, but you did take this big old loop to get there. If I take this finger and I go from here to here, and sorry, from your perspective, it'd be to the left. I've gone 10 centimeters to the left. Which one went further? And what's weird about that is that this path is longer, but this path winds up further from where it started. So in effect, this one actually has a greater end result. And that's sort of the big difference between our first two sets of vocab words, aside from, I suppose, position. Which is that total distance traveled, or just distance traveled, is going to be how far someone or something actually moves. It's going to include any backtracking that's happening. It's going to include any turning. It's going to be including basically everything. And when it does that, what you're describing isn't how far you are from where you started. It's not a set of instructions to make the same end result happen. It's talking about what happened in the middle. So the middle part of the process of your travel. That's the bit that total distance traveled actually talks about. For example, if I just tell you that I go 30 meters, you'll know how far I walked. You'll know, you could probably use that to figure something out about how long the actual trip took, but you wouldn't necessarily know where I wind up. You'd know the furthest I could wind up away is 30 meters, and that is worth noting, but beyond that, I could be anywhere within a 30-meter radius circle. If we're then talking about displacement, what that one is, and the word displace is part of that, meaning to move from one location to another. Instead of just keeping track of the distance that you've gone, what displacement is tracking is a straight line of the distance and direction from the start point to the end point. And you can also think of that as the path you could take to get the same end results while moving in a straight line. This is not always the same thing as the total distance traveled, because people don't always go in a straight line, basically. Or objects don't always go in a straight line. And what that's describing isn't what happens in the middle, it's describing what happens as a result of that motion. So let's say we've got a situation where we start here. It's a little too large. Let's say we've got a situation where we start here and we end here. And if we travel on a path like this, then our total distance traveled would be this distance here, which let's say is 10 meters. And that would be the entire distance along the squiggly line, which I should probably move my face so it's not covering up the 10 meters bit. If I then take this and I'm instead looking at this line right here, what this line right here would show me is how to get from the start to the end, and saying, well, this is the result of what you did. And in this case, that looks something like along the lines of, I guess if this is 10, it's probably somewhere around 5-ish meters. But the problem is I can't just say 5 meters, because again, that'll sort of do this thing where you've got this radius going around it. If I want to actually describe the motion that happened, and the result of what happened includes a direction. So I would need to have something along the lines of some angle from some reference point or some reference line saying that this is, actually it's probably closer to like 10, 15 degrees. 10-ish degrees above the x-axis would be my direction, and then the distance would be 5 meters. If you look at that 10 meters for the distance traveled, it's in a bunch of different directions, right? You can't really say it's in any specific direction. So very explicitly, distance traveled does not include a direction, displacement does. Times that this is going to be different are pretty much if you turn. They'll technically always be different because the displacement will always include a direction, I guess, unless you don't move, in which case they're both 0 and there's no direction on 0. Times this could be different would be technically any time, but the time where the numbers will be different will be anytime you turn or anytime you turn around. They're really similar, if not the same, to each other if you're traveling in a straight line, but the displacement will still include a direction. What's interesting about this is that if we want to try to code that direction within the numbers that we're using and actually keep track of it, we're going to need something new. Because numbers you're used to, something like saying 5, just abstractly 5, is that it's counting something, right? It'll tell you how many of a thing there are. It'll tell you how big something is. But what it won't do is tell you which direction it goes. We need a new way to store information that actually includes that direction as well as how big it is. And this... oh, I don't have it on here. I suppose a later slide will be talking about what a vector is. Just kidding. I am pretty sure I forgot to include that in any of the ones for APC. I will remember that. All right. So instead, once we've done that motion, how do we describe the actual process itself? Well, we can describe the distance we went, but there's more to it than that, right? If I start here and do that, versus if I start here and do that, those two were very different processes, even though they had the same displacement and the same distance traveled. So we need another way to talk about it. And if you're describing, if you're describing the results of a motion, that would be distance or displacement. If you're describing the process of moving and what motion is currently happening, that one's going to be getting into things along the lines of speed and velocity. So anytime you say fast, what that's meaning is that if you wait a small amount of time, you will travel a large distance. If you say slow, what that means is if you wait a long amount of time, you will travel a small distance. You could also think of this as, if I wait a second, how far will the thing move? Or the rate of change in your current position, which should be ringing some calculus alarm bells for you right now. So what words do we use to describe how fast we're moving? Well, pretty much just fast or slow. I guess in particular, like speed is the big one. But sometimes speed isn't the only thing that matters. So if I tell you that I'm trying to go from Boston to Florida, I guess. If I tell you that I'm going 100 miles per hour, if I was going in a straight line, you could maybe try to figure out how long it took, but there's kind of a problem because if I'm going 100 miles per hour north versus going 100 miles per hour south, there's going to be very different results on how long it takes. And so you really sometimes also need to know which way something's moving. So those are two aspects of any time we're talking about the way something moves. The first of which is going to be the speed it's going at. The second of which is going to be which direction it's going. When you hear 20 miles per hour, hopefully that should give you a hint about how this works to some extent. It's telling you that you are going 20 miles in a given hour. So again, it's literally telling you how far you go within a set time frame. This does make some assumptions about that being constant, but 9 meters per second would be the units we use. For reference, those two speeds are the same as each other. It's 1.1 times meters per second. 2.1 will give you times meters per second will give you roughly miles per hour. So if you just take any speeds we have in this class and double them, that'll get you speeds you're probably more used to. So speed versus velocity. Speed is the distance that your position changes by each second. It's the rate of change in your position and just the rate. Basically, it's just how fast you're going, slow you're going. Velocity, on the other hand, is not just the rate of travel, it's the rate and direction of travel. And so if you have this will make more sense when we learn what a vector is, but if you have a position vector or an equation that is a vector equation for a position, and you take your time derivative, meaning your derivative with respect to time, of that equation, what that will give you is an equation for velocity. So the derivative with respect to time of position as a function of time is going to spit out velocity as a function of time. Another way to say this is that position prime is equal to velocity. That does come up occasionally. It's not raised to the first power. It's prime if you're using sort of Newton notation. College Board does not use Newton notation, but you can, and especially for the units where we're just doing the relationships between position, velocity, and acceleration, saves a lot of writing to just do prime instead of dt. But when we do start doing other derivatives, you can't just do the prime symbol, so knowing how to do both can be helpful. What's different between the velocity and the speed is literally just that the direction is there. Any velocity is actually going to include a speed within it. So they are very closely related. The way that they get particularly different is if you're talking about average speed versus average velocity, because those are describing different things. But in basically every other case, they're hyper closely related to each other. So then let's start thinking about how that changes. Because if we have two people and we're trying to figure out which one of them is going to win a race, the information we've described so far still won't do it. If I tell you that one person is 10 meters away from the finish line and going faster than the other person right now, and the other person is 20 meters away from the finish line, we still don't actually know, and they're both going in the right direction, we still don't actually know who's going to win. Because it's possible that those speeds will change in such a way that one person will finish before the other. And so we really need to also be able to pay attention to the way that the movement's going to change. There are three big ways that can happen. You can speed up, you can slow down, or you can turn, which would be changing the two different components of velocity. You can either change the speed component by speeding up or slowing down, or you can change the direction component by turning. In physics, every single subsection of that, speeding up, slowing down, and turning, are all called acceleration. So our vocab word for this is acceleration. It's the rate and direction in which you change how you are moving. Again, this is a rate. So if you take the time derivative of velocity, you'll get acceleration. So v prime, which is the same thing as the second derivative of position with respect to time, gives you acceleration. So doing that again, the second derivative with respect to time, meaning you're taking the derivative twice and it's over dt squared, of position, gives you velocity, but you have to take a derivative of velocity after that. So dv dt, and that will give you acceleration. All of these are as a function of time. If you don't have it as a function of time, this will not work. So just be careful with that. Mostly because when you take a time derivative, when time isn't one of the variables, you either have to take a partial derivative, assuming everything else is held constant, in which case you'll get... I shouldn't talk about multivariate yet. It would probably help for something later down the line eventually, but I think I'd rather not overcomplicate it. Another way to think of acceleration is it's the amount your velocity is going to change by each second. So when you're thinking about the units in particular for this one, if I say that my acceleration is 10 meters per second, literally what that means is every second, take whatever your velocity is, add or subtract 10 from it. That's it. The way we tend to write those units are meters per second squared for the sake of saving time. So meters per second squared, or meters per second to the -2 is, I believe, how the College Board writes it sometimes. Same thing. So again, there are three options for this. You can either speed up. The thing that will cause something to speed up is if you have a positive velocity. Positive and negative are going to be what determines directions within one dimension. But more, and we'll get to that more later, hopefully. I'm just realizing I probably didn't even include this stuff later, but hopefully, fingers crossed. If your velocity is in a specific direction, every second what your acceleration is doing is saying, take this arrow, take this number, take this amount, pop it on top of that thing. If they go the same way as each other, they're working together, and you'll be building arrows on top of arrows, so you'll get a progressively bigger arrow. If you start out with one arrow going in one direction, this is our velocity vector, and our acceleration goes the other way, what that does is it says, okay, take this arrow, push it backwards by this amount. The way you do that is you make it smaller. So you'd be like, all right, well, now it's this big. Do it again. Now it's this big. Do it again. Now it's this big. And that will make you slow down. The one thing that's weird about when acceleration is going the opposite way as when you're moving is it'll make you slow down until eventually you'll stop. If the acceleration is still going the same direction, then you'll be starting from nothing and saying, okay, well, we started with something like this. We added something going the other way and it became nothing. Let's add something going this way again. And when we do that, Now every time we do it, it'll get progressively bigger. And that's because all of a sudden your acceleration matches the direction of the velocity. So if they're opposites, it'll slow down until it stops, then they'll become the same direction, then they'll speed up. Turning will happen, and we'll get to this in way more detail later, but turning will happen anytime your acceleration is perpendicular to the way you're moving, or if there is a piece of your acceleration that's perpendicular to the way you're moving. If you've already watched all of Unit 0 for some reason, if you have a perpendicular component of your acceleration vector to your velocity vector, it will turn. So taking a sec to talk about these things in some sort of more concrete examples. Pause, think about these, give it a shot. I'll just sort of talk about answers after that. So what does it mean for a position to be constant? Well, if your position is constant, then you're not changing where you are, which means you're not moving. If that's true for an extended period of time, then that also means you're not changing how you move. And so your time derivative with respect to position would be 0, or your rate of change with respect to where you are would be 0 because you're not changing, so your velocity would be 0. If it's staying that way, your acceleration will also be 0. If your velocity is 0 currently at a given point in time, that means your position is not changing. You could, however, still be changing what that you're doing. You could be stopped very briefly, for example, to turn around, or at the very beginning of motion. Which means that you could still have an acceleration even if your velocity is 0. If your acceleration is 0, what that means is that your velocity, whatever it is not changing. Now that could mean that you're not moving at all, because that would mean that your velocity is 0 and staying 0. If your acceleration is 0 and you have a non-zero velocity, though, it means that you'll keep going in that same direction forever at that same rate. Constant velocity is different from constant speed in one big particular way, and it's based around the difference between speed and velocity in general. Speed doesn't include direction. Velocity does. If you say that you have a constant velocity, it means you're not turning. If you say you have a constant speed, who knows? You could be doing anything as long as you go the same number of meters each second. If you say that an object is traveling at a constant 20 meters per second, what that means is that each second it will go 20 meters. So in the first second, it goes 20 meters. In the second second, it still goes 20 meters. But if I say something along the lines of an object is traveling 20 meters per second while accelerating forward at 5 meters per second squared, because it's traveling forward and accelerating forward, I start at 20 for my velocity. Each second, I add 5 to that. So I would start at 20 at time 0. At 1 second, I need to take that and add 5. So I would be going 25 meters per second. At 2 seconds, I would have added 5 twice, so I would be at 30. At 3 seconds, I would have added 5 3 times, and so I would be at 35. And so what's going on here is we're literally just taking our acceleration number and tacking it onto our velocity number each second. And when they line up with each other, that's all you got to do. When they're opposites, you would be subtracting it. So progressively, we'll be going faster and faster and faster, which means that between the 3rd second and the 4th second, we'll be going further than we did from the 1st second to the 2nd second. Yeah. That should be a decent place to start with the vocab. There aren't book problems for this one. Not really. So I hopefully have included a worksheet. Go for it on that. Let me know if you have questions. Goodbye, YouTube.